Hello, I'm Roman, and welcome back to the series of videos Neural Networks from Scratch in Golang. I'm using this book, Neural Networks from Scratch in Python, but I'm not using Python, I'm using Go, as you can guess from the name of the series. Why I'm using Go? Because why not? And in the previous video, I finished finally with the chapter 10 that is called Optimizers. We've been implementing several different optimizers for the model training, and right now we have 4 of them. We have the optimizer, stochastic gradient descent with momentum or without. Then we have the RMC prop. Then we have come on. Then we have Adam, which is the best one, the one that we implemented, and we have Ada and Adam. And so we've finished with the optimizers, and right now, as the chapter 11 says, we go into test it with out of the sample data, whatever that means. So let's go. Up to this point, we've created a model that is seamlessly 98% accurate at predicting the testing dataset that we have generated. Well, I don't have 98, I have 94. But, I mean, in general, it's a pretty accurate model. This generated data are created based on a very clear set of rules outlined in the spiral data function. It's true, and I have it too. This is the one. The expectation that a well-trained neural network can learn a representation of these rules and use this representation to predict classes of additional generated data. So the idea that if I train the model, then I can take 2 values, pass it through the model, and it should predict in which set of the values it corresponds. Imagine that you have trained a neural network model to read license plate on vehicles. The expectation for a well-trained model in this case would be that it could see future examples of license plates and still accurately predict them. The prediction in this case would be correctly identifying the characters on the license plate. So it's actually something like optical character recognition model. The complexity of neural networks is their biggest issue and strengths. By having a massive amount of tunable parameters, they are exceptional at fitting to data. This is a gift, a curse, and something that we must constantly try to balance. Overfitting is... not fitting the data, okay. With enough neurons, a model can easily memorize a dataset, however, it cannot generalize the data with too few. This is one reason why we do not simply solve problems with neural networks by using the most neurons or biggest model possible. I think that it's actually interesting. What if I will, no, instead of having 64 neurons, I can have 10 times bigger, right? And let's see what will happen. Well, we hit the accuracy pretty fast, and I think it will stay the same. Yeah, it's kind of started to jump back and forth. And the reason, I think it just memorized most of the data set. I think it's 97% already. With a very small loss value. I'm not sure if it can fit 100% accuracy, I think, but I assume that if I will add twice more or 3 times more neurons, it can memorize it fully. So I think this is the part where they talk about having a balance between not using the biggest possible model. At the moment, we are uncertain whether our latest neural network's accuracy is due to learning to meaningfully represent the underlying data generation function or instead overfitting the data. So in the first case, we assume that the model can learn the rules and not the data. It means that if we will give a new data, it will predict the class correctly, while the overfitting means that the model is really good at memorizing this specific data set, but once you try to predict something, for example, in this case, once you try to predict the values that are outside of the training data set, most likely it will give some garbage result. At least this is my understanding. So far, we have only tuned hyperparameters to achieve the highest possible accuracy on the training data and have never tried to challenge the model with the previously unseen data. Overfitting is effectively just memorizing the data without any understanding of it. Yeah. An overfit model will do very well predicting the data it has already seen, but often significantly worse on unseen data. Good generalization on the left side and overfitting on the right side. So you can see that the line is kind of blurry and more smooth. So for example, in the red part, you can see that there are still blue dots, while the overfitting draws this very complex and accurate shape. I mean, accurate without any blur. So it's very distinct. And for example, if you, especially when, for example, this part is interesting. The left image shows an example of generalization. In this example, the model learning to separate red and blue data points, even if some of them will be predicted incorrectly. So most cases will be predicted correctly. One reason for this might be that the data contains some confusing samples. When you look at the image, you can see that, for example, some of these blue dots might not be there, which would raise the data quality and make it easier to fit. A good dataset is one of the biggest challenges with the neural networks. The image on the right shows the model that memorize the data, fitting them perfectly and ruining generalization. Without knowing if a model overfits the training data, we cannot trust. Without knowing if a model overfits the training data, we cannot trust the model result. For this reason, it's essential to have both training and the testing data as a separate site for different purposes. Training data should be used to train models. The testing or out of the sample data should be used to validate a model's performance after training. We're using the tested data during the training later in this chapter for demonstration purposes on. We're using the testing data during training. Okay. The idea is that some data are reserved and withheld from the training data for testing models' performance. And I actually have seen even even more complex. So instead of having 2 buckets of the data, you could have 3 buckets of the data, the training and testing that are used during the model. And then you have a separate, additional set of the data that model never saw at all. Because, well, at least what I saw during the study of the fast.ai course and using the different, well, I used FastAI, which is built on top of the PyTorch. And the reason that it splits the data, I think 80% and versus 20%, 80% of the data is used to train the model, 20% is used to evaluate the model during the training loop. But still, this 20% has influence on the model training because there are still some, what's called, metrics that have been calculated using these testing data. And I remember they were talking that you need to have the data that is not used anyhow in the training process at all. So you can actually evaluate how the model performs. But, well, let's see. I think that these guys are way smarter than me in this area. So, but I'm just passing the information that I observed before. In many cases, one can take a random sampling of available data to train with and make the remaining data that. In many cases, one can take random sampling of available data to train with and make the remaining data the training set. This is what I've been talking. You kind of split the data that you have in two buckets. You still need to be very careful about the information leaking through. One common area where this can be problematic is in the time series. Consider a scenario where you have data from sensors collected every second. You might have millions of observations collected, and randomly selecting your data for the testing data might result in samples in your testing dataset that only a second in time apart from your training data. Those are very similar. This means overfitting can spill into your testing data, and the model can achieve good results on both training and the testing data, which won't mean it generalized well. So you, for example, you have a time series data, and you just cut the last 20% of the data, and you can still have the training data, the testing data that are very close to each other, and the training data that is very close to each other. Both datasets must differ enough to prove the model's ability to generalize. In time series data, a better approach is to take multiple slices of your data, entire blocks of time, and reserves those for testing. Other biases like this can sneak into your testing dataset, and this is something you must be vigilant about, carefully considering if the data leakage has occurred and how to truly isolate out of the sample data. In our case, we can use our data generation function to create new dataset that will serve as out of the sample testing data. We can, but I think in this case, it will use the same dataset because of the way the neural networks from scratch Python model that is used here. It kind of replaces the randomization function, and I think this will return the same, but in my case, it will actually return a new dataset if I call it second time, because I have the same, when I run every time the model training that I have here, it generates the really new dataset. Given what we just said about overfitting, it might look wrong to only generate more data, as the testing data could look similar to the training data. Intuition and experience are both important to spot potential issues with out of the sample data. By looking at the image representation of the data, we can see that another set of data generated by the same function will be adequate. This is just about as safe as it gets for out of the sample data, as the classes are partially mixing at the edges. Also, we are quite literally using the underlying function to make more data. With the data, we evaluate the model's performance by doing a forward pass and calculating loss and accuracy the same as before. So we have basically we're running it again. So we're calculating the loss and the predictions based on the different number of the data, right? And do we need to do the same number of the epochs? No, I don't think so. Epochs. Okay, and the validation accuracy and the loss. While 80% accuracy and the loss of 0.858 is not terrible, this contrasts with our training data that achieved 98% accuracy and way smaller loss. This is evidence of overfitting. In the following image, the training data is deemed and the validation data point are shown on top of it is the same position for the both well generalized and overfit. We can recognize overfitting when testing data results begin to diverge in trend from training data. It will usually be the case that performance against the training data is better, but having training loss differ from the test performance over 10% approximately is a common sign of serious overfitting from our anecdotal experience. Ideally, both datasets would have identical performance. Ideally, I think it still have some deviations, but yeah, maybe something less than 10% is the key. Even a small difference means that the model did not correctly predict some testing samples, implying slight overfitting of the data. In most cases, modest overfitting is not a serious problem, but sometimes we hope to minimize. Let's see the training process of the model once again, but with the training data, training accuracy, and loss plot dimmed. We add the test data and its loss and accuracy plotted on top of the training counterpart to show the model is overfitting. Prediction issues on the tested data overfit model. I guess dots is the training data or testing data, and this is a classic example of overfitting. The validation loss falls down, then starts rising once again. The model starts overfitting, and I think, for example, here I had the same, right? So yeah, wait. No, it's going down. Oh no, yes. No, it's actually went down most of the time, but the accuracy started to jump. The dots represented the classes in the validation data can be spotted over areas of effects of other classes. Yeah, we can see that, for example, this blue dot from the testing data goes into this green area. Previously, we weren't aware that this was happening. We were just seeing very good training results. That's why we usually should use the testing data to test the model after training. The model is currently turned to achieve the best possible score on the training data, and most likely the learning rate is too high. There are too many training epochs, or the model is too big. There are other possible cases and ways to fix this, but this is the topic of the following chapter. In general, the goal is to have the testing loss identical to the training loss, even if it means higher loss and lower accuracy on the training data. Similar performance on the both dataset means the model generalized instead of overfit. So yeah, in this case, for example, we will have less accuracy, like less stable accuracy, but it will be generalized. So it will learn the rules of the data rather than data itself. And it will perform with the same accuracy on unseen data. But with overfitting, the overfitted model works very good on the training data and works really bad, well, most likely bad on the new data. As mentioned, one option to prevent overfitting is to change the model size. If a model is not learning at all, one solution might be to try a larger model. If your model is learning, there is a divergence between the training and the tested data, it could mean that you should try a smaller model. One general rule to follow when selecting initial model hyperparameter is to find the smallest model possible that still learns. So we want to have smaller model. Other possible ways to avoid overfitting are regularization techniques we'll discuss in chapter 14 and the dropout layer explained in the chapter 15. Often the divergent divergence of the training and testing data can take a long time to occur. The purpose of trying different model setting is called hyperparameter searching. Initially, you can very quickly, usually with a few minutes, try different settings like layer size to see if the model are learning something. If there are, train the model fully or at least significantly longer and compare results to pick the best set of the hyperparameters. I mean, this was always, some not an unclear thing, but there is always some sort of the randomization that you cannot influence in training the model, and the only thing you can do is just to guess and try to set different hyperparameters. And as far as I can see, there is no way, well, maybe there is, but I mean, there is no way to prove and make a rule I mean, there is no rule how you can calculate the best hyperparameter for the model training. It's always like you need to try this and this, or maybe you need to try a smaller model, or maybe you try a bigger model, or I don't know, start with this learning rate. So yeah, that's interesting. Another possibility is to create a list of different hyperparameter sets and train the model in the loop using each of those sets at a time to pick the best set at the end. The reasoning here is that the fewer neurons you have, the less chance you have that the model is memorizing the data. So the more neurons we have, the easier it will be to just remember the concrete values. Fewer neurons can mean it's easier for neural network to generalize, actually learn the meaning of the data compared to memorizing the data. With enough neurons, it's easier for neural network to memorize. Remember that the neural network wants to decrease training loss and follow the path of least resistance to meet that objective. Yeah, I mean, for the neural network, it's actually, it's easier to just remember the data than learn what are the rules inside this data. Our job as the programming is to make the path to generalization part easier, not to the memorization. This can often mean our job is actually to make the path to lowering loss for the model more challenging. I think that was the quickest chapter in this book. I'm thinking, should I implement this forward paths? Yeah, I think I should, because even, I mean, I do understand what it means, but I want to, I want to try it. Okay, so what we need to do, we need to create X test and no, test data test classes, and it should be dataset spiral data, again 103. Then actually testing the model, right? Then we take in the dense one, we call in the forward, what dense one forward, we using the test data, right? Then we take in the first activation, and then we take in the dense output. I'm curious, is there a way to make it in a loop and don't? Probably it is. I mean, apart from the loss activation function, I can create an interface for the layer and for the activation function that has a forward method. Then I can form an array and do something like this. I will leave it for now. Let's see. But that might be a case. Then we have loss activation forward. And we take in the output from the second one and we using the test classes. And this is our validation loss, right? Declared but not used. And then I need to calculate the test accuracy, right? Test accuracy, which is loss, I think calculate accuracy. We have predictions in the, where we have predictions. Loss activation, no. Loss activation output and test classes. And then we can print finally the result. So we have the validation, right? So the loss value is, where is it? Validation loss. Then we have accuracy, which is test accuracy, right? Let's train. Let's see. Okay, so for this run, we have a pretty high accuracy, like 89, 84%, with loss something like 0.1. But with the new data that we generated, we have a loss of 0.81 and the accuracy of 80%. So this is the very big difference. And I think this is what it's been talking, that in this case, most likely model remembered all of the data. But for example, okay, let's play around. What if we change for 16, right? 16 layers. Will it make a difference? Loss is really big, accuracy 51%. But the accuracy on the tasting data is 47 and the loss is pretty high. So probably it's not big enough. Okay, and there is still a question of the other hyperparameters. Well, what just happened? Interesting. Okay. Let's try another one. We have accuracy of 86, accuracy and 73, loss is much bigger, like twice bigger. So probably it's not the issue just with model size. Probably it's an issue with the hyperparameters that the optimizer is using. And the question is, what optimizer is actually it's better to use? Because from the previous chapter, it was told that in some cases, the classic stochastic gradient descent with the momentum would perform better than the Atom. Or we might using too many epochs. So a lot of the things to consider, and to be honest, I have no idea how to, start. I can spend some time just randomly changing the values, but I don't like this approach, and I hope there is a better way to do this. Or maybe there will be just, already known good starting point for specific problems and the data and so on. But still, I guess or maybe there is a way to actually find a good, I can, no, for example, I can train for 1 day because this model is really small, and I can Now, create a set of the different params, like for example, change the number of the layers, change some of these params, and just go in the loop and checking the results, and then pick up the set of the values when difference between the validation accuracy loss and the training loss is the smallest. And I don't know, I can put it for the training for 1 day and just experiment. That might be the case, but I'm wondering, I believe there are better approaches than the one that I'm just, coming, just thinking right now. So let's take a look. No, chapter 12. What was the previous testing now? This. In the chapter on optimization, we used hyperparameters tuning to select hyperparameters that lead to better results, but one more thing requires clarification. We should not check different hyperparameters using the testing dataset. If we do that, we're going to be manually optimizing the model to the test dataset, biasing it towards overfitting this data, and these data are supposed to be used only to perform the last check if the model trains and generalizes it. We should not check different hyperparameters using the testing data. So this is what we actually been doing. For example, we've been changing, these parameters based on results that are printed here. But ideally, well, as the book says, and the common sense right now, we should check we should adjust hyperparameters based on this, based on how the model performs on the testing data, not on the training data, right? Those hyperparameters tuning using the test data is a mistake. This test dataset should only be used as unseen data, not informing the model. The test dataset should only be used as unseen data, not informing the model in any way which hyperparameters tuning is, other than to test performance. Hyperparameters tuning can be performed using yet another dataset called validation dataset. Okay, so we have the testing dataset and the validation dataset. Yeah, this is what I've been talking in the beginning of the video, like 3 buckets: testing, training, test, and the validation data. The test dataset needs to contain real out of the sample data, but with the validation dataset, we have more freedom with choosing the data. So I guess in the testing, I'm just thinking, maybe it's incorrect. We can take the training data, we can slice it into training data and the testing data that is used for training, and then we create a validation dataset, which would be very different, but we will use it to actually challenge the model's performance. If we have a lot of the training data, can afford to use some for validation purposes, we can take it as, if we have a lot of the training data, we can afford to use some of the for validation purpose, we can take it as out of sample dataset, similar to test dataset. So yeah, if we have a lot of the data, we can slice it in 3 buckets. We can now search for parameters that look best using this new validation dataset and test our model at the end using the test dataset to see if we really tuned the model or just overfitted it to the validation data. Not sure I follow. We can now search for parameters that work best using this new validation data. Okay, there are situations when we will be short on data and cannot afford to create yet another dataset for the training data. In those situations, we have 2 options. We cannot afford to create yet another dataset for the training. The first is to temporarily split the training data into smaller training set and a validation set for hyperparameters tuning. After, with the final hyperparameter set, train the model on all of the training data. We allow ourselves to do that as we tune the model to the part of the training data that we put aside as the validation that keep in mind that we still have a test data set to check the model's performance after training. Interesting. So we have a data, we split it, we train the model. Well, we train the model to find the best hyperparameters. Once we found them, we combine those two buckets together. We train the model with knowing that those hyperparameters are the best for generalization. Interesting. The second possibility in situation where we are short on data is a process called cross-validation. Cross-validation is primarily used when we have a small training set and cannot afford any data for validation purposes. How it works is we split training dataset into a given number of the parts, let's say 5. We now train the model on the first 4 chunks and validate on the last. So far, this is similar to the case described previously. We are also only using the training dataset that can validate on data that were not used for training. What makes cross-validation different is that we then swap samples. For example, if we have 5 chunks, we can call them A, B, C, D, E. We may first train on A, B, C, D, then validate on E. We will then train on A, B. Oh. Okay, so we will train for the number of the chunks using the new chunk every time as the validation. Yes. We'll then train doing this until we have validated on each of the 5 sample groups. This way we do not lose any training data. We validate using the data that was only used for training during any given iteration and validate on more data than if we just temporarily split the training data set and train on a. This validation method is often called k-fold cross-validation. Here our k is 5. Here's an example of 2 steps cross-validation. So we have training data, we have 5, we split it into 5 buckets. So then we feed the model on the 4 of them, validate on E, then this, and 3 more times. 2 smallest chapters in this book. I'm not even sure which one is smaller. When using a validation dataset and cross-validation, it is common to loop over different hyperparameter sets, leaving the code to run training multiple times, applying different settings each run, and reviewing the results to choose the best set of the hyperparameters. In general, we should not loop over all possible setting combinations that we would like to check unless train is exceptionally fast. It's usually better to check some setting that we suspect will work well. Yeah, we suspect will work well. Pick the best combination of those settings, twin them to create the next list of the training setting, next list of setting sets, and train the model on the new set. We can repeat this process as many times as we would like. Training data, we split it, A, B, C, D, E, then we use an E as the validation set. Okay, so the training, validation, and the testing. I'm just trying to remember correctly the terminology. Yes, and the dates. Okay. What's additional? Nothing here yet. Okay, thanks. Training data. Well, hopefully. Okay, let's read it through. Since we're talking about, looks like this series will be just me reading and trying to understand all of the things. And I think it will, after this, all of the new materials, I will need to sleep to properly digest all of the things for the next chapter. And what is the next chapter? L1 and L2 regularization, and okay, finally we see some code. So let's just read and finish with this one. Since we are talking about dataset and testing, it's worth mentioning a few things about the training dataset and operations that we can perform on it. This technique is referred to a preprocessing. However, it is important to remember that any preprocessing we'll do to our training data also needs to be done in our validation and testing data later to predicted data. Neural networks usually perform based on data considered on numbers in the range of 0 to 1 or -1 to 1, with the later being preferable. Centering data on the values of 0 can help with model training as it attenuates weight basing in some direction. Models can work fine with data in the range of 0 to 1 in most cases, but sometimes we're going to need to rescale them to a range of -1 to 1 to get training to behave or achieve better results. For example, with some neural networks that work with images, usually for example, the image is set of the bytes where each color represents a value from 0 to 255, and you can represent any color component as kind of integer value from 0 to 255, or you can represent it as from 0 to 1 with a fraction, which then you can multiply by 255 and you get an integer value for the color component. And I remember that all of the models that I've used before to integrate usually works with the float numbers. Not all of them, but okay. Many activation functions behave properly within this described range. For example, softmax outputs a vector of probabilities containing a number in the range of 0 to 1. Sigmoid also has an output range from 0 to 1, but 10 outputs a range from -1 to 1. And I think that's the question of what the activation function is the best in a certain case. Another reason why this scaling is ideal is a neural network's reliance on many multiplication operation. If we multiply by number above 1 or below -1, the resulting value is larger in scale than the original one. Within this range, the result becomes a fraction, a smaller value. Multiplying big numbers from our training data with weights might cause floating point overflow or instability. Weights grow too fast. It's easier to control the training process with small numbers. There are many terms related to the data preprocessing standardization, scaling, variance scaling, mean removal, nonlinear transformation, scaling to outliers, etc. But they are out of scope in this book. We're only going to scale data to range by simply dividing all the numbers by the maximum of their absolute values. For example, of an image that consists of the numbers in the range of between 0 and 255, we divide the whole data set by 255 and return the data in a range from 0 to 1. We can also subtract 127.5, which is the middle, to get the range. This one, then divide by this value, and we will have the -1 to 1, which actually expands, expand the range. So you could have now twice larger fraction for the same value, if it makes sense. We need to ensure identical scaling for all the dataset. Same scale parameters. For example, we can find the maximum for training dataset and divide training, validation, and testing data by this number. In general, we should prepare a scaler of our choice and use its instance on every dataset. It is important to remember that once we train our model and want to predict using new samples, we need to scale those new samples by using the same scalar instance we use to the training, validation, and testing data. For example, with the images, if we'll go, for example, to this scale from -1 to 1, then we should do the same for example, if we want to run a neural network against the image, we should convert or either this into this one or this one based on how it was trained. In most cases, when we're working with the data, sensor data, we'll need to save the scalar object along with the model and use it during the prediction as well. Otherwise, results are likely to vary, as the model might not effectively recognize this data without being scaled. Even the resulting numbers slightly outside of the range, it does not affect validation or testing negatively, since we do not train on this data. Additionally, for the linear scale, we can use different datasets to find the maximum as well, but be aware that non-linear scaling can leak the information from other datasets to the training dataset, and in this case, the scaler should be prepared to on the training data only. I'm not sure I get this one. In cases where we don't have many training samples, we could use data augmentation. For example, I've seen that when you need to, I don't know, train an image classifier, you have some data, but then you can slightly modify the image. For example, change the brightness, change the perspective a little bit, and for the model it will look like a new image, and it still can learn the features for this one. One easy way to understand augmentation is in case of the images. Let's imagine that our model's goal is to detect rotten fruits, apples, for example. We will take a photo of an apple from different angles and predict whether it's rotten. We should get more pictures in this case, but let's assume that we cannot. What we could do is to take photos that we have, rotate, crop, and save those. Yeah, this way we have added more samples to the dataset, which can help with model generalization. In general, if we use augmentation, then it's only useful if the augmentations that we make are similar to the variations that we could see in the reality. For example, if you will stretch the image vertically 3 times, I would not expect an apple to be that long. But for example, make image a little bit lighter or darker, or change the color, so the apple will be a little bit different in colors. That might work, I think. For example, we may refrain from the using the rotation when creating a model to detect road signs, as they're not being rotated in real life scenarios. You've never been in my hometown. The case of rotated sign, however, is one you better consider if you're making a self-driving car. Yeah, but I mean, most of them correct, but sometimes you could have some damage signs, which shouldn't be the case, but sometimes happen. Just because a bolt came loose on the stop sign and flipping it over doesn't mean you no longer need to stop here. How many samples do we need to train the model? There is no single answer to this question. One model might require just a few per classes, and another may require a few million or billion. Usually a few thousand per class will be necessary, and a few tens of thousands should be perfect to start. The difference depends on the data complexity and the model size. If the model has to predict sensor data with 2 simple classes, for example, if an image contains a dark area or does not, hundreds of samples per class might be enough. To train on data with many features and several classes, tens of thousands of the samples are what you should start with. If you are attempting to train a chatbot that intricacies of the written language, then you're going to likely want at least millions of samples. That's a lot. Okay. And the chapter 14. I will stop for today because I think there are a lot of the new information that it's better to be digest after some sleep. And I want to tell that I officially passed 50% of the book. And it took me around 32 episodes. So I assume that will be the same number to finish the book. Table But if I take a look at the how many chapters are actually left, there is 1, 2, 3, 4, 5, 6, 7, 8, 9. So in chapters, it's actually less than half. I think closing is just, telling the good words. And what I can do next. But slowly, but I'm going towards the end of this book and learning new skills and recording the video on the main channel about this challenge that I'm kind of recording here. Thank you for watching, and I see you tomorrow. Bye-bye.